Hello everyone. In this video, we will be discussing in detail about electrical discharge machining, electrode feed control mechanism, dielectric fluid, whatever we are using and its property, all those things we'll be discussing in this video. So, first we will start with the electrical discharge machining, electrode material. So, electrode material should be such that it would not undergo much tool wear when it is impinged by positive ions. The localized temperature rise has to be less by properly choosing its property, or even when temperature increases there would be less melting. Further, the tool should be easily workable as intricate shaped geometric features are machined in electrical discharge machining. Thus, the basic characteristics of electrode material are it should be high electrical conductivity. It means electrons are cold emitted more easily and there is less bulk electrical heating. And next one is high thermal conductivity, that is for the same heat load the local temperature rise would be less due to faster heat conducted to the bulk of the tool and thus the tool wear. Next property would be higher density for less tool wear and thus less dimensional loss or inaccuracy of tool. And next is high melting point. So high melting point leads to less tool wear due to less tool material melting for the same heat load. And next would be easy manufacturability and cost. It is very cheap. And some of the electrical materials, electrode materials which are used commonly in the industries are graphite is the like a very common electrode materials which is highly sensitive to the current, and electrolytic oxygen free copper. So this is again a new metal which is not easily available only for this particular process. This particular material is usually made by some other process. And next one is tellurium copper, which is nothing but 99% of the copper and 0.5% of the tellurium. Again, tellurium is very sensitive to the current. And next one is the brass. So, and apart from that, like we have a few more materials, but usually that is not recommended because in olden days they used to use that particular metals, but later they got to know through the research and many operations like only these metals is exclusively used for the present machining processes. So among the these metals whatever I have listed, that of course graphite is the most common because of its fair wear characteristics and easy machinable properties. And even small flush holes also can be drilled into this graphite electrodes, which is a little difficult maybe with other copper and other materials what we discussed, tellurium, other things. And copper has also good EDM wear and better conductivity. So based on the availability and the cost, we can go with that. And it is generally used for better finishes in the range of like a 0.5 micrometer. And copper tungsten and silver tungsten are also used for making deep slots under poor flushing conditions, especially in tungsten carbides. It offers high machining rates as well as low electrode wear. Copper graphite is good for cross-sectional electrodes. It has better electrical conductivity than graphite, while the corner wear is higher. So brass ensures stable sparking condition and is normally used for specialized applications such as drilling of small holes where the high electrode wear is acceptable. And moving to the electrode movement, that is the electrode feed mechanism. So in addition to the servo controlled feed, the tool electrode may have an additional rotary or orbiting motion. Electrode rotation helps to solve the flushing difficulty encountered when machining small holes with electrical discharge machining. In addition to the increase in cutting speed, the quality of the hole produced is superior to that obtained using a stationary electrode. Electrode orbiting produces cavities having the shape of the electrode. The size of the electrode and the radius of the orbit, 2.54 mm maximum, determine the size of the cavities. Electrode orbiting improves flushing by creating a pumping effect of the dielectric liquid through the gap. And we can able to see the servo feed mechanism of an electrode wear. So this is the tool electrode and this is the final shape, and this is the corner wear which we are calling it denoting as the LC, and this is the initial shape of the electrode tool, and this is the side wear where it is clearly shown. This is the side wear, and this is nothing but end wear. The point from the initial to the final, whatever it is, this is nothing but end wear, and end wear we are denoting it as LE, and side wear we are denoting as LS. And as usual, this is the workpiece where the crater has been formed, you can able to see, and the machine depth we are denoting it as capital D. So the corner wear ratio is nothing but D by LC, side wear ratio is D by LS, end wear ratio is D by LE, and volume wear ratio is nothing but VM by VE. And VW is nothing but volume of the workpiece removed, and V is nothing but volume of electrode consumed. The melting point is the most important factor in determining the tool wear. Electrode wear ratios are expressed as end wear, side wear, corner wear, and volume wear. So no wear EDM when the electrode to workshop wear ratio is 1% or less. Electrode wear depends on number of factors associated with EDM like voltage, current, electrode material, and polarity. The changing shape of the tool electrode due to the electrode wear causes defects in the workpiece shape. Electrode wear has even more pronounced effects when it comes to micro machining applications. The corner wear ratio depends on the type of electrode. The low melting point of aluminium is associated with the highest wear ratio. And this is the electrode wear for the different materials. Among that, the aluminium stands on the first with the corner wear ratio percentage of 700. You can able to see. For the zinc, it is around 500. For the brass, it is around 200. Copper almost 200, and steel is around 150 to 180. Graphite, you can able to see graphite hardly like a 20-30 like a corner wear ratio, and copper tungsten again less than 10 percentage, silver tungsten again less than 10 percentage. And moving to the graphite, electrode wear. So the graphite has shown a low tendency to wear and has the possibility of being molded or machined into complicated electrode shapes. So the wear rate of the electrode tool material and the wear ratio are given by Kalpakjian in 1997 with the formula Wt equal to 11 to 10 power 3 into I into Tt power minus 2.38. So Rw is equal to 2.25 into Tr power minus 2.3, where Wt is the wear ratio of the tool in millimeter cube per minute, and I is nothing but EDM current in amperes, and Tt is nothing but melting point of the tool electrode in degrees Celsius, and Tr is nothing but ratio of the workpiece to the tool electrode melting points. Then moving to the next topic in this video, that is electric discharge machining dielectric. In electrical discharge machining, material removal mainly occurs due to the thermal evaporation and melting. As thermal processing is required to be carried out in the absence of oxygen, so that the process can be controlled and oxidation avoided. Oxidation often leads to poor surface conductivity, that is electrical of the workpiece, hindering further machining. Hence, dielectric fluid should provide an oxygen-free machining environment. Further, it should have enough strong dielectric resistance so that it does not break down electrically too easily. But at the same time, it should ionize when electrons collide with its molecule. Moreover, during sparking, it should be thermally resistant as well. Generally, kerosene and deionized water used as dielectric fluid in EDM. Tap water cannot be used as it ionizes too early and thus break down due to presence of salts as impurities occur. Dielectric medium is generally flush around the spark zone. It is also applied to the tool to achieve efficient removal of molten material. The three important functions of the dielectric medium in EDM process are: insulates the gap between the tool and the work, thus preventing a spark to form until the gap voltage are correct. Cools the electrode workpiece and solidifies the molten metal particles. Flushes the metal particles out of the working gap to maintain ideal cutting conditions. Increase metal removal rate. It must be filtered and circulated at constant pressure. And the main requirements of electrical discharge machining dielectric fluids are: adequate viscosity, high flash point, good oxidation stability, minimum order, low cost, and good electrical discharge efficiency. For most EDM operation, kerosene is used with certain additives that prevent gas bubbles and deordering. Silicon fluids and a mixture of these fluids with petroleum oils have given excellent results. Other dielectric fluids with a varying degree of success include aqueous solutions of ethyl glycol, water in emulsions, and distilled water. And next topic, that is the EDM flushing, that we can discuss in the next video because it will take more time to discuss. So we'll discuss in the next video. Thank you.